I now call to order the Society's 2,440th meeting in the 150th year since its founding on March 13th, 1871. Good evening, everyone, and welcome to PSW Science's Spring 2021 Meeting and Lecture Series. Because of COVID-19, the Society is bringing this meeting to you via Zoom from locations all around the globe, rather than our usual home, the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C. Our speaker tonight is Tony Tyson, Distinguished Professor of Astronomy at UC Davis and Chief Scientist at the Rubin Observatory. He will be speaking to us about astronomical observations and interference from satellite constellations like SpaceX's Starlink. I'm Larry Milstein, President and Program Director of PSW Science, one of the oldest scientific societies of Washington, D.C., founded in 1871 as the Philosophical Society of Washington, to provide a forum to exchange scientific ideas, further scientific understanding, and encourage scientific inquiry. This lecture is being recorded and will be posted to the PSW Science YouTube channel, where it will join over 160 other recordings of PSW Science meetings and lectures. We invite you to explore these presentations and to subscribe to the PSW channels on YouTube and Vimeo, as well as to PSW on Twitter and Facebook. And please, like the programs that delight you. PSW Science is a membership organization, and a participatory membership is central to PSW Science's mission of communicating and furthering science. It's easy to join. Go to the homepage on the PSW Science website, www.pswscience.org. Click on the blue Join button at the upper right-hand corner and follow the prompts. The Society is grateful for the sponsorship of the 2020-2021 lecture series by the Policy Studies Organization in cooperation with the American Public University and by a donor who asked to remain anonymous. And we're also grateful to the sponsor of tonight's lecture, PSW member Tim Thomas. Please join me in thanking our sponsors. Before we turn to tonight's lecture, in keeping with the Society's traditions, we will welcome new members and read the minutes of the previous meeting and the summary of the previous meeting's lecture. I am pleased to announce that Tony Tyson, our speaker tonight, has been elected to the Society. Tony learned of PSW through our invitation to speak, and his interest will be clear in some small part from tonight's lecture. Please join me in welcoming Tony to membership. Welcome. Membership is an important part of the Society. I encourage everyone with an interest in science to become a member. PSW Science is a 501c3 charitable education and professional organization. Dues payments and other donations are tax deductible. Recording Secretary James Heelan will now read the minutes of the 2,439th meeting and the lecture by Simon Bennett and Dan Irwin on digitally building the new Cross-London Underground Elizabeth Line, one of the largest infrastructure projects in Europe. James, the screen is yours.
Thank you, Larry. On April 23rd, 2021, by Zoom webinar broadcast on the PSW Science YouTube channel, President Larry Milstein called the 2,439th meeting of the Society to order at 8:03 p.m. Eastern Daylight Time. He welcomed new members, and the recording secretary read the minutes of the previous meeting. President Milstein then introduced the two speakers for the evening, Simon Bennett and Daniel Irwin from Crossrail Limited. Bennett is head of learning legacy, and Irwin is the geospatial lead. Their lecture was titled Crossrail, Building the £15 billion Elizabeth Line, Digitally Digging a New Metro Beneath London's Skyscrapers. Bennett began the presentation by introducing Crossrail, the project to build the Elizabeth Line, a new 42-kilometer railway under the center of London. The line will connect the existing surface railways to the east and west of the city. Built in 1863, the Metropolitan Line was the first underground rail in London. In 1988, England opened its first national railway. Planning for Crossrail began the next year. Following decades of study and parliamentary approval, construction began in 2009. The purpose of the new line is to relieve crowding on the existing underground and to decrease journey times through the city. Crossrail is now Europe's largest construction project. It involves massive underground spaces, 50 kilometers of track, and wide 250-meter-long platforms. Once completed, the route will be known as the Elizabeth Line. Crossrail uses two methods of tunnel construction. Platform tunnels are created by a sprayed concrete lining method and construction of a platform structure. Running tunnels are created by a boring machine that erects concrete rings as it goes. Irwin then described the project's building information modeling. Crossrail's biggest challenges have included navigating London's underground infrastructure. For the project's tunnels to thread the eye of the needle, Crossrail required extremely accurate modeling. Using London's survey grid, Irwin said Crossrail was able to achieve an approximately 5 mm margin of error. Crossrail maintains a common data environment comprised of 3 primary data sets that will be used to run the completed infrastructure: graphical models, non-graphical data, and an electronic document management system. The graphical models include more than 4 million design files built around computer-assisted design standards that allow them to be easily overlaid. Irwin then showed 3- and 4-dimensional project models and described their technical details. Crossrail has compiled non-graphical information on approximately 600,000 assets as the project has progressed. The Asset Information Management System, or AIMS, is inside the Document Management System, allowing engineers to relate assets to documents. Crossrail began using the Uniclass standard, but eventually moved to Asset Data Dictionary Definition Documents, or AD4. Irwin then described how the AIMS categorized information and streamlined project maintenance. Crossrail used Enterprise Bridge software to manage approximately 6 million documents. The software additionally managed contracts, asset breakdown structure, and other workflows. The master data model was created in-house midway through the project to control naming and codification among different systems, link graphical models and non-graphical data, and model data integration. Irwin then addressed the benefits and lessons learned from creating the common data environment. He said it gave engineers visibility before construction began, detected clashes between models, and ensured that the work of disparate teams did not adversely impact one another. The common data environment also allowed for innovations such as Bluetooth low-energy beacons, augmented reality, virtual reality, on-site document verification, virtual information structures, smart boards with collaborative model use, and mobile GIS. Realized benefits included improved construction safety, improved data quality, and easier access to data. Bennett then returned to the screen. He attributed the project's delays to ensuring the interoperability of the railway's systems and ensuring that floating slab tracks are properly installed to reduce vibrating surface structures. Crossrail is running a new signaling system that also needs to be synced to the existing systems in the railways that it will connect. Train cars are being constructed with full-length walkway and air conditioning, and these new trains are longer than existing tube trains, requiring stations across the network to be lengthened. The project is now in the commissioning and handover phase. 2 stations, Custom House and Farringdon, have already been handed over to TfL Rail as station operator, and railway service has begun. All but one of the remaining stations will be handed over by the end of this year. The railway's central section will open in 2022 and will be fully opened by early 2023. Bennett said Crossrail created a less than expected environmental impact and preserved archaeological sites. He is now working on the learning legacy to educate successor projects on Crossrail's lessons learned. The speakers then answered questions from the online viewing audience. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. President Milstein adjourned the meeting at 9:57 p.m. The temperature in Washington, D.C., 16 degrees Celsius. Weather, clear. And number of concurrent viewers on the Zoom and YouTube live stream, 85. And views on the PSW Science YouTube and Vimeo channels, 259. Respectfully submitted, James Heelan, Recording Secretary.
Thank you, James. The minutes will be posted to the website in due course. Please send any corrections or comments on the minutes to corresponding secretary Robin Taylor at correspondingsec@pswscience.org. A video of the lecture is available for everyone without charge on the PSW Science YouTube channel, the PSW Science Vimeo channel, and it can be accessed directly from the PSW Science website. We now turn to tonight's lecture. It is my pleasure to introduce tonight's speaker, Tony Tyson. Tony is Distinguished Professor of Physics and Astronomy at the University of California, Davis, and he is Scientific Director at the Rubin Large Synoptic Survey Telescope Observatory. He served as Director of the observatory for a decade before becoming Chief Scientist. And before that, he was a member of the physics division at Bell Laboratories. Tony was a pioneer in applying CCDs to astronomy, and early in their use, he discovered and studied faint blue galaxies. He then pioneered the field of weak gravitational lensing, creating maps of dark matter using their gravitational effects on the appearance of these distant blue galaxies. His current research is on the nature of dark matter and dark energy. Tony is a fellow of the American Physical Society and the American Academy of Arts and Sciences, and a member of the National Academy of Sciences and the American Philosophical Society. He earned a BS in physics at Stanford and a PhD in condensed matter physics at the University of Wisconsin. All questions will be fielded in the Q&A session after the lecture. Tony, the screen is yours.
Okay, thank you, Larry, very much for that kind introduction. And I look forward to the Q&A session at the end of this. And I'm very pleased to join you tonight to talk about an important topic, which is the industrialization of space. Before I do that, however, I have to share my screen. Okay. Okay. You folks see that?
Yep, you're good, Tony.
Okay, thank you. Okay, so you're all aware of the fact that there's an exponential rush to space by a number of companies launching satellites in low Earth orbit for various purposes, among them offering wideband internet with low latency to everywhere, pretty much everywhere in the world. This, of course, has plus sides to it, but it also has a minus side, a big one, for both radio and optical astronomy. And I'm going to talk to you tonight about some of the impacts that we think it's going to have on astronomy generally and the Rubin Observatory in particular. Go on to start with describing this observatory, but then go on to measurements and simulations that we've done on the impact, and then talk about mitigations. So this is a simulation of the march of time, an exponential increase in the number of satellites as a function of year, done by AGI, and it shows it's based on a notional number of satellites from FCC and ITU filings. It's approximately correct, but of course not exact. especially as you get out to the out years. And the challenge, of course, is that the night sky will be, well, pretty much crawling with all of these things. They're actually fairly bright. They're big and bright, and they're low. And they radiate kilowatts. And you're going to have to look through them in order to do science. So this is a challenge. I first heard about this from rumors on the, wait a second, let me back up. I first heard about this from rumors on the social media. One of the issues here is that is the increased number of possible collisions of satellites. And so here you see basically spatial density plot versus altitude, operational altitude. And this is actually a fairly old plot, but it does show that there's a large, growing number of possibilities for collisions. And I think that by the time you get to 50,000 satellites, for example, which is the best estimate that I've heard recently for the next few years anyway, the chances of a actual runaway, the so-called Kessler effect, increase. And so you see here, for example, a couple of examples of collisions. The Iridium Cosmos collision, the Chinese ASAT test. And so you can follow this density, the number of objects in space. This is from the NASA orbital debris data from this year. And it plots the number of monthly number of objects in low Earth orbit by object type. And so you can see rocket bodies down there out of control and tumbling, mission-related debris, various spacecraft, fragmentation debris, and you see some of them are re-entering, and the total number of objects. And you can see that up here on the right, they're running away, and this is actually going to be an exponential for quite some time. So that's the challenge. Here is a slightly different view of this, where the number of tracked satellites versus altitude is plotted. And you can see that there's this increased density, as I showed you before, around 500 to 1,200 kilometers altitude. But then recently, of course, from all the Starlink launches, there's a spike here at 550. And actually, this is data from March. Now, a couple of months later, this number has gone from 900 Starlinks to 1,300 Starlinks operating at 550. So I first heard about this, as I mentioned, through social media in May of 2019, and I reached out to SpaceX and said, let's talk engineering, not politics, not policy, but engineering, and see what we can do jointly about trying to dim these satellites. This picture is taken on the Blanco 4-meter telescope in Chile. The field is a little under 2 degrees wide. And this is about 150-second exposures, 150-second exposure, and 19 of the recently just launched Starlink satellites passed through the field of view during that 150-second exposure. And this just gives you an example of some of the unlucky possible moments that you would have in optical astronomy with another factor of 10 more than these. So here's a graphic showing some of the components of the Rubin Observatory. In the middle is our telescope. It's an 8.4 meter telescope. It's squat and short because it has to move very fast to point to new places in the sky in 5 seconds. It has a 3200 megapixel camera, which is shown not to scale on the left. And that is up here suspended underneath the secondary mirror. It actually has 3 mirrors. The light comes down, reflects off of an annular primary down here, up to a secondary, and then down to a tertiary mirror, and then into the camera. Each image is 10 square degrees, which is about 40 full moons. We will be scanning the sky with 2,000 images per night, each 15 seconds or so, over 10 years, starting in 2024 early, effectively making a digital color motion picture of the universe down to around 25th magnitude. We will catalog from all those observations 37 billion stars and galaxies. And each night, we will find something that moves or changes its brightness, flashes or whatever. And there will be 10 million of these alerts, we calculate, 20 terabytes of data every single night. And so you can imagine that there are a number of different science cases, of course, that went into justifying this facility. It does something totally new in astronomy. And so the idea, of course, is that it will, like any completely new facility, it will discover unanticipated things. We try to anticipate it in a 600-page science book, but of course, as you all know, adventures in instrumentation like this often discover something that's not in the science book. Anyway, the impact of bright satellite trails varies depending upon science case, and I'd love to chat with you during Q&A about the various science cases that are affected more or less by these satellites. So this was the observatory back a couple of years ago. We hadn't completed the dome yet. And on the left is a spectroscopy facility that we built in order to look at the spectrum of a bright star, a bright hot star in a field, each field that we're observing as we observe it, to back out the atmospheric absorption spectrum. But then COVID hit, and I'll show you in a minute what happened as a result. But before that, somebody went into the dome and opened the shutter of a nice big view camera and exposed for a few hours and got this really fantastic image looking up through the superstructure of the uncompleted dome. So as I mentioned, we had to vacate the summit in March of 2020, a full power shutdown, nobody allowed. And we have lost approximately 15 months on the project. As a result of that, we're pretty much back on schedule now. And this is the dome a few months ago. It is now completed, and we're working inside on the telescope itself that's being put together inside of the dome. You can get a scale from this by looking at these big trucks down here. It's a big facility. So the survey that the Rubin Observatory is going to undertake, the so-called Legacy Survey of Space and Time, is a wide, fast, deep survey in the sense that it looks at a very large field, a wide field of view of the sky. It tiles the sky, as I mentioned, every night with 2,000 exposures. Fast in the sense that you have 15 seconds of time resolution, and deep because we're going eventually to 27th magnitude, which is, a typical Hubble deep field limit, over the entire visible southern sky, about 20,000 square degrees. And so, as I mentioned, we're going to have a survey of about 37 billion objects in space and time. As a result of this, each patch of the sky will be visited over 800 times, and there will be 30 trillion measurements total. It turns out that it's a rather largish database, about 200 petabytes or so, but that's not uncommon these days. What is uncommon is what we want to do with that, which I will get into. One of the things that we want to do is to automate the discovery of the unexpected. It's so much data that you can't have graduate students pouring through this anymore. You have to engineer software that will look for something that is not expected. This turns out to be useful for other purposes, mainly for quality assurance. And so we would have to do this anyway in order to maintain the quality of the survey. But we're going to be looking for things in both the static images and the alerts that we issue every night that are out of the ordinary and cannot be easily expected by known objects. This is a picture of the camera. It's a drawing of the camera, rather, cutaway drawing showing the focal plane here and a red filter cutaway in front of it. We can get about five filters in this can of the camera at a time. 5 of the 6 filters that we're going to be using, all the way from the ultraviolet to the near infrared. This whole camera weighs about as much as a SUV and is about as large. The focal plane layout is shown on the right here. There are 189 4K by 4K CCDs, each of which is split into 16 individual subsegments, each with its own output amplifier. So you have a lot of streaming video data coming out. This whole thing gets read in 2 seconds. So a half a megahertz, 16 times 189 times half a megahertz. A lot of data coming out during that 2-second read. The moon is shown here for scale. So what happens if you take a look at the focal plane? If you have a satellite pass across the focal plane, which happens, we compute, which will happen if you have 50,000 of them, at least 1 or 2 times in each exposure. Even if we would attempt to avoid them. And you can see that it hits probably 15 or so CCDs. The rest of them are fine as long as the satellite isn't so bright that it causes blooming, which is a problem with really bright satellites, of course. And so the issue is, what is this actually going to do to the camera and the electronics and the images themselves? To do that, we had to get a sense for how bright these satellites were. And so this is way back in 2019. I went, Todd Borison very kindly at Las Cumbres Observatory took this picture and many others of some early satellites, 0.9s of SpaceX satellites. And when you look at the photometry here and then extrapolate it to our 8.4 meter mirror and our big camera, it worked out to be close to the saturation level of the charge coupled device, which of course alerted us to a problem that we had to investigate in the lab, namely the response of our charge coupled devices to such a bright trail. This is a result of doing that. I have a lab where I test these CCDs. And so this is a so-called Starlink trail, a Starlink slit that is re-imaged onto the CCD, that really bright thing here, going from upper left to lower right. And then you see a bunch of electronic echoes of it. This is due to the small capacitive crosstalk among those output video amplifiers. And there are 16 of them on the CCD, and you can see that there's a bit of a crosstalk. And so armed with this information, then we could calculate how faint you had to make the satellite in order that we could then grapple with these large crosstalk residuals, images, and get rid of them, model them out and subtract them. And so we did quite a lot of work on that. And this is the result. So this is a plot of surface brightness measured in electrons per pixel in the camera as a function of the satellite apparent magnitude going from 0th to 7th. Remember, you can probably see 6th magnitude fairly easy in a nice little dark site, not in New York City, but if you go somewhere else. And there are people, I actually know people who actually can see 7th or 8th magnitude. And so 7th magnitude is considered the limit of human vision. And it just turns out, just by accident, that we think that we can correct this crosstalk if the satellite were pretty much dimmer than 6.5 magnitude. 7th magnitude would be a goal. And so that's a weird coincidence. The human eye has nothing to do with the Rubin Observatory LSST cam, but so be it. And so these trails, which I mentioned to you, of course, are rather bright. They're up here near saturation. And so a lot of work had to be done to dim the satellites, will have to be done to dim the satellites sufficiently so that we can be assured that we can correct all of these 189 times 16 channel crosstalk pairs. Take pairs of all of those. It's a lot of data. So another idea, which we considered for a while, it was a charming idea. Mainly, why don't we try to avoid them? So suppose that the satellite operators gave us all of the information on position and time of all of their satellites. And suppose we knew that precisely before we opened the shutter for the next exposure. And so we have an algorithm that calculated what we should do. Should we wait? Should we move a little bit to somewhere else? So this plot here shows only 10 minutes in a simulation of roughly 50,000 satellites during twilight, during late twilight. 10 minutes of these satellites. And the number of streaks is on this color scale on the bottom. Yellow is lots of streaks per unit area. One of the programs that we're pursuing, that the scientific community is pursuing with the LSST survey, is to detect and get orbital information on possible Earth-threatening asteroids. To do that, you want to observe in twilight, pointed towards the setting or rising sun. And you can see that there's a big challenge if you're over here trying to do that job. So that's a fairly big impact on the site, on that particular project. But you would think that, well, you know, there's some places where you might be able to point here that aren't too bad. The problem is that the cadence of our survey is so rapid. We can't spend more than a couple of seconds to move to the new place in the sky because we're moving out the camera in that 2 seconds, and we have to be at a new place in just seconds. So the fast cadence of our survey means that we can't take advantage of these places on the sky. And so we did a further simulation to see if we could see what actually would happen to an algorithm like that. And so take a look just at the blue histogram here. Plotted here are the number of observations in just 3 days of the LSST survey. Number of observations as a function of the altitude of the sun below the horizon. So over on the right is twilight. This is civil twilight going to astronomical twilight here. And you can see that you can get roughly 100 or so observations. But then if there are only 12,000 satellites, which is what we're going to be having just this next year, if all of these companies do what they have filed to do, the number of successful observations drops by over a factor of 2 using this algorithm of just waiting until it clears and then opening the shutter. And then it gets worse, of course, as it gets hopeless from there. So it's a wild goose chase that actually didn't work, I think. So that doesn't work. And so we're working with SpaceX. The astronomical community actually is working with SpaceX to try to solve these light pollution effects, both in optical astronomy and frankly in the radio as well. As I mentioned in that plot, making the spacecraft about 10 times darker may remove some of the satellite trail artifacts, these crosstalk echoes in the electronics. In our camera, we're actually working with SpaceX to follow up their experiments at darkening these test satellites in future launches. And as you have probably heard, they are treating the near Earth orbit satellites as an advanced laboratory in which they try out different techniques of darkening their satellites. If that is completely successful, that is to say, if it gets down to around 7th magnitude or so, we think that we can get rid of most of the electronic artifacts, the non-linearities of our camera and our detector. But even if we do that successfully, the main trail will still be there, and it will be bright compared to anything that we're observing. Typically, the brightness of these trails is somewhere around a few 100 million times brighter than the typical objects that we are studying. And so that's bright. You can probably attempt to mask it out, but there's spillover flux, which I'll show you an example of. And so this limits the data. This really seriously complicates data analysis and limits scientific discoveries. So here's an example of their first attempt. This is called DarkSat. So on the top picture, you see the bottom of the bus. Those microwave phased arrays, 4 of them actually look white. And what they did is that they blackened them. And this satellite here was launched, and it was called, of course, DarkSat. And sure enough, it was about a factor of 2.5 in flux. These are magnitudes here. So a magnitude is about a factor of 2.5. These are 4 ordinary Starlinks and DarkSat here. And so DarkSat worked. Unfortunately, it also heated up their transmitter and got too hot. And so their phased arrays got too hot. And so they tried something different. And it's a nice, clever idea, which is to deploy a sun shield, a visor at release, at altitude, which shields the sun from hitting these phased arrays. And so a number of visor sets have been launched. What you see in this picture, you're looking at the bottom here of the bus, and the sun is coming here and hitting these visors, and their shadow, they cast a shadow on the antennas. This is about 3 meters across, and the solar panel, which you see here, is 9 meters high. So this is a large satellite. So it turns out that this works pretty well. And the next slide shows an example from a lot of data that was taken. So this is the number of observations of a Starlink satellite. And this is before darkening. This is before anything, before DarkSat, before VisorSat. And you see the mean apparent brightness is about 5th magnitude. This is something you can easily see in the dark site, by the way. And this is, of course, too bright for us. And then over here in blue are a bunch of measurements that have been made more recently of one particular VisorSat satellite. And it's in this particular case, they've managed to reduce it to about 6.5 apparent magnitude, which is really great. And so they're on a roll to 7th magnitude. They're continuing to do experiments. There are other pieces of hardware on the satellite that reflect sunlight, and it's a very complex problem. And so we're trying to work with them on that, following up their observations. One of the things that they're going to do, that they're planning on doing, is modifying their operations. And so, for example, when they're on station, they have this visor or its successors. They're working on better ideas even today. But they can adjust the solar array angle so it's hidden behind the chassis. So the solar array reflects some sunlight, and so they can hide it as it passes over your observatory. When they launch the satellites, as you know, they launch them into a lower orbit somewhere around 300 kilometers. And to do that, it's so low that there's friction in the atmosphere. And so they can't deploy their solar array in the L configuration, as you see up here at the top. So they have it deployed in the velocity direction. And that, of course, can reflect a lot of sunlight down onto your observatory. And so what they can do is to roll the satellite knife edge to the sun to minimize the reflected light. So they're toying with these various ideas, and they should be variously effective. Another interesting thing is that when we simulated all of these effects, we simulated it, of course, with the 8.5 meter mirror on the Charles Simoni telescope of the Rubin Observatory. And that mirror is large enough that the low Earth orbiting satellites, particularly at 550 kilometers, are actually slightly out of focus. And so instead of having a nice focused cross-section, this is what you would expect from a star, for example. It's widened in this particular pattern. At least we predicted it would be. And sure enough, we went and got some data, which I will show you momentarily, from a very nice big telescope in Hawaii built by the Japanese called the Subaru telescope, and looked at a similar satellite. And sure enough, we saw that exact same pattern with the appropriate size. So they're slightly out of focus, which is actually a good thing in some sense, but a bad thing in another. Mainly the satellite trails are actually wider. And so this is an example of a satellite, I think it was around 5th magnitude, taken on the Subaru telescope, Hypersa Prime Cam. And it's the old Fuse 1 satellite, which is about the right size. And so this is the picture. You can see a couple of muon events in the camera here. And so if you take a cross-section across that satellite trail, so this is a cross-section of the surface brightness across the trail, on a linear scale, it looks, well, just sort of like what you would expect from the combined size of the satellite and the atmosphere and the telescope aperture. But if you take the same data on a log scale, which is actually more interesting, you see that the satellite trails have these very wide wings on them. And this is partly due to the fact that it's a little out of focus, and partly due to the fact that there's a lot of turbulence in the atmosphere. And we're going to be looking, and so these are in these crazy surface brightness units that I like, of electrons per pixel in the camera. And the typical galaxy, for example, that we're looking at in our survey is going to be less than 10 electrons per pixel. And you can see that you're looking at an arc-minute wide swath of sky that we would have to mask out. So the area adds up. Along the trail, the satellites actually vary in flux. This is due to the fact that various different pieces of the satellite reflect variously at different angles. And that, and here's the Fuse satellite on the right. You can see all this MLI here reflecting sunlight and little bits changing with time. And you can see that it does do that. One of the other things, and so this, by the way, is just a hint that this could cause bogus alerts in our alert stream. Of those 10 million alerts per night, we could have possible bogus alerts because of these things varying, glinting, suddenly imitating a bogus object. But occasionally you can get these really bright flares. And we've seen quite a lot of these recently from the existing 1,300 satellites that are now at station. And so down at the bottom here is Arcturus, basically 0th magnitude star. And here's a bright flare, much brighter than Arcturus from a Starlink that is just has the right or maybe wrong solar angle relative to the sun and your observatory. And these are going to occur many times per night with 50,000 satellites up there. So here's an even bigger problem. Mainly, as you probably have heard, some companies such as OneWeb are placing their satellites at at higher altitudes, around 1,200 kilometers. And so this is a plot done by Pat Seitzer, which shows if you took just 10,000 satellites and you place them either at 500 kilometers or at 1,000 kilometers, what do you expect to see in terms of the number of satellites visible as a function of hour during the night? And you can see that if you put your satellites around 500 or 600 kilometers, you can see during twilight, you can see some of them, both evening and morning twilight. But if you placed your 10,000 satellites instead at 1,000 kilometers, they are visible all night long, particularly in the summer. As a result, all of the dark sky observations are affected, not just the twilight observations. And so this is really damaging to optical astronomy, putting satellites at high altitude. It's also a dangerous thing to do because it will take centuries for them to decay if something goes wrong, whereas it's just years for something to decay and fall back to Earth at these lower altitudes. So there's a couple of disadvantages to that. We had a big meeting called Satellite Constellation #1 a while back, and SatCon 1 came up with a bunch of recommendations. One is the no-brainer: darken satellites in all phases of the orbit, including launch, parking orbit, and final orbit and decay. Darken them to fainter than about 7th magnitude. And that, by the way, corresponds to something, if you're building one of these satellites, corresponds to something you can actually build to, mainly a radiance of about 44 watts per steradian at 550 kilometers. And so you can get out your slide rule and try to build something that has that radiance or less. Fewer satellites, lots of luck, but that would help. And as I mentioned, satellites on orbits as low as possible, and no satellites at 1,200 kilometers. We also would benefit by having very high accuracy orbit information for other purposes. It's sort of hopeless for us at the Rubin Observatory to use, but other big telescopes, and there's some really big ones being built, could make useful use of this if they had actual orbit prediction TLE data. And then I know a couple of folks that are working on this. It's sort of cool. An app for getting predictions in advance of the position and time for these satellites, and actually for their brightness also. So that will be very nice if that happens. And there's no reason why it shouldn't. There are GPS on each one of these satellites. And then we're going to be working, of course, the whole community on advanced algorithms, machine learning algorithms for avoidance of bright satellites. But as I mentioned, that's really a wild goose chase, in my opinion. And then I mentioned this predictive model for satellite brightness versus orbit. I think that's coming down the pike, and that'll be terribly exciting and very helpful for us. Then finally, this is just beginning. The scientific community has not really come to terms with this. And they're just beginning to realize that, frankly, there are going to be real challenges in the data reduction, and they're really not prepared for this. And as a result, we need to pour a lot of effort into full end-to-end forward simulations of each science case and the impact of these of these satellite constellations on each one of them. And so that's just starting. I have a few students working on that on one particular problem, but I know that there are a few others around the world, but it's a small effort and it needs to be organized better, in my opinion. And so we have this new paradigm. The new paradigm is, and this is true of all areas of science, from genomics to astronomy, and that is that it used to be that we were limited by our finite data sets. You know, we all remember the grand old days of plotting your data point by point and fitting some kind of curve to it. Even within the last 10 years, we were limited primarily by observational selection effects, small data sets. But now we're talking about huge data sets, billions of objects. And the statistical error is going to be small as a result. And the systematics actually are really the biggest error. And so our science is really limited by systematics. And these satellites in both space and time create such systematics, as I tried to show you. And so one of the conclusions that we reached in SatCon 1 was that with tens of thousands of these LEO sats, generally we found no combination of mitigations that could completely avoid the impacts of the satellite trails on the science of any observatory, including ours. So our observatory is actually designed, I originally called it the dark matter telescope, to probe the dark sky in totally new ways, to understand dark matter and dark energy, the nature of the time-varying events in the sky, to unprecedented faintness. It's basically the Hubble limit over the entire visible sky. And this, unfortunately, definitely requires fewer and fainter LEO sats in order to realize the full scientific potential. So there's some next steps. We're continuing to work with industry to develop joint operation solutions to minimize the science impact. Mentioned some of that. Tools for efficient scheduling would be useful, maybe more for other observatories than ours, but we will continue to attempt to improve that. Predictive luminosity models are going to be extremely important. Maybe you just want to avoid or dodge the really bright ones that cause blooming in your camera. That's probably only a few thousand satellites per night. And if you had predictive models for that, you could avoid them, I think, or a large number of them. Then develop observing strategies for new kinds of data analysis methods to partially correct for these, both the statistical and systematic effects caused by these residual trails. That we're not going to eliminate the trails. We might, if we're lucky, we'll eliminate all of the electronic echoes, but the trails themselves will, of course, still be in the data. And then explore science impacts of these residuals via full end-to-end simulations. And so these are our homework assignments for the next year or two, or three. But, you know, very frankly, these kind of efforts on our part are not exponential as a function of time. We don't have an exponentially large growing budget, and we don't have an exponentially growing number of postdocs and graduate students. But the industry that is pushing this business opportunity in space is exponential with time and with expense. And so that's the problem. You have a linear process versus an exponential process. This is a picture of about 1 part in 10 million of the Rubin Observatory LSST survey sky that was done on a supercomputer. This contains all of the known physics that we know in the instrument and in the atmosphere and in the universe. In a full simulation, it goes to 27th magnitude. And this is a very small postage stamp, very small piece of the sky, as I mentioned, 1/10,000,000th of the full LSST survey. So it's a lot of rich information. It's going to be exciting in both space, as you can see here, and also in time. And so one of the neat things about this picture is that if you go deeper and deeper and look at the fainter and fainter galaxies, you're actually looking back in cosmic time to a redshift of about 3. And so there are two aspects to the word time in the name of our survey. There's that aspect, and there's the aspect of looking for things that are changing on 15-second timescales and longer. That is going to open up new windows that have been unexplored so far to our universe, and we're going to, my guess, we're going to discover the unexpected. So that's optical astronomy, and I wanted to close by mentioning some issues in the radio. And so this is again a picture of the bus in a Starlink satellite, and you can see in this picture a few other ones that show this L configuration with a 9-meter high solar panel developing many kilowatts of power, and then kilowatts of RF being radiated from these microwave arrays. Kilowatts in the presence of extremely sensitive radio astronomy receivers that are looking at nanojanskis on the ground, about a factor of 1 billion fainter in terms of spectral density than the radiation from this. And so you don't even want to have this radiation going into a side lobe of your radio antenna on the ground. The side lobes maybe are down by 30, 40 dB. That's not enough. You need 100 dB. So as you know, the Federal Communications Commission and the International Telecommunications Union regulate the radio from space. And so the spectrum of the radio is allocated. And in fact, as you can see, this is a tiny snippet from the full spectrum. This only goes from 9.2 gigahertz to about 15 gigahertz. And the spectrum all the way up to 200 gigahertz is oversubscribed. As you can see here, at each frequency, there are so-called services that are shared. And so you have the amateur radio service sharing spectrum with other things, some of them actually satellites. And you see here this little tiny yellow thing called radio astronomy. And that's right here. That's the only little piece for radio astronomy in this this snippet of the spectrum. And it even there is shared with other services. And so where is Starlink? This is the radio astronomy area, if it's free of interference. And here is the SpaceX transmitters on the Starlink satellites right next door. Well, when you build radio transmitters for under a finite budget, it's really very difficult to have 100 dB of attenuation in the outband outside of your allowed spectrum. And so here I indicated some of the frequencies that have been allocated to Amazon Kuiper and to SpaceX. There are a lot of other players in this game, including the other countries, including the Chinese, and they're populating a large part of the spectrum. This is just one little snippet. There are total, by the way, of about 19 of these little radio astronomy windows that the FCC and the ITU have allocated to passive scientific use. But increasingly, unfortunately, in radio astronomy, technology marches on, and discoveries in recent years have moved on from looking in just these little windows of the spectrum to using the whole spectrum all at the same time at once to look at new phenomena that cause a radio chirp, for example, that moves through the spectrum. And so recent advances in radio astronomy have gone to lower flux levels, nanojanskis and sub-nanojanskis, and also monitoring, if you can, the entire spectrum all at once. Well, this is going to be hard, as you see. And increasingly, by the way, there are active radars now being launched, only some of which are regulated by the FCC. Some are not, which brings its own problem. So, for example, here is some, on the left, for example, is where you might want to do radio astronomy. And so this is say, regulated by the FCC. And on the right is where you can transmit from your satellite. And if you would build a real world transmitter and output network and feed it into your array, the energy gets splatters off of your assigned frequency band into the astronomy band. It's just a fact of life. And so what the FCC has done is to say, okay, so we're going to ask you, we're going to rejigger the frequency assignments in this particular case and introduce a guard band. And so what they have done in this particular case, not all of them, is to introduce a guard band so that SpaceX and OneWeb and others that are broadcasting here at 12.7, they left enough room for the flux to get down to lower levels. Unfortunately, probably not low enough. But again, this is a piecewise band-aid, which probably is going to be difficult for other reasons to institute across the entire spectrum. So that's my presentation, and I look forward to questions and answers, or at least questions.
Well, thank you, Tony. We have time now for Q&As. Zoom participants can raise their Zoom hand or type their question in the Zoom Q&A panel. I'll call on Zoom participants in turn to unmute their mic and ask their question. If you're a Zoom participant and you want to ask a question, but you don't want to ask it out loud, just say that in your text question in the Q&A panel, and I'll read your text out loud. YouTube viewers can text questions in the YouTube chat box. The text questions asked on YouTube will be conveyed to me, and I will read them aloud for everyone to hear. So let's start with our Hubble repairman, John Grunsfeld. John, can you unmute your mic and ask your question? If not, I'll read it.
Hi, Tony.
Hey, John.
I just read the FCC ruling.
Yes.
Whatever, 57-page ruling. And from reading that, it says that basically SpaceX is working well with astronomers and all is good.
Yeah.
Do you have any comments? Have you seen that report, and do you have any comments on that?
I did. And to me, that's not the most interesting part of that ruling, but yes, they did say that. And I think the answer, I have to agree that I wouldn't say all is good because we're not to 7th magnitude yet, but I have to hand it to them. They have a team, an engineering team that's working hard on this and working with us. And they're treating space as an advanced laboratory. They're making piecewise improvements on their albedo of these satellites, and so they're moving in the right direction. I think that they're actually setting an example for these other companies. The part of that ruling that I found most interesting is that, as you know, the FCC does not regulate the optical. You can launch, if you wish, a 10 gigawatt laser and point it at the ground, and the FCC is perfectly happy with that. They only regulate the radio. But in that ruling, they did say that they are aware that these satellite constellations can cause damage to astronomy. And as you know, John, actually, the Hubble has had a lot of photobomb exposures recently because the Hubble is just below these satellites, and they're very close and very bright. And so
it wasn't below when I last left it.
Oh, okay. So there have been, yeah,
it's a decaying orbit, of course.
Yeah, there have been several recent Hubble exposures that were photobombed. But what I found interesting about that ruling actually was that they said that that these industries should do all they can to avoid interference with astronomy. That's the first time I've ever heard the FCC say anything like that.
That's very promising.
I think it's sort of I wouldn't say a foot in the door, but it's promising, John. That's right.
And you said a very good thing, which is SpaceX is setting an example that they're working with us in the astronomical community. I think China's plans are for 13,000 satellites and Japan about 3,000. And China also has a ground-based astronomy program. Do we have any insight at all into what they're thinking?
Yeah, I have a friend, several friends there actually that I talk to. Science and everything else is managed in China quite differently than elsewhere, and so it's if you get the if you get the right person to talk to, you're way ahead. And so they're interested not only in the impact on their ground-based astronomy, RF impact, and also on their spectroscopy, but also they are launching a new space station, and they're going to be tethering to it a new observatory, sort of Hubble-like, but only different observatory, and those folks are worried about this as well. So
of course,
there are conversations occurring in China.
Okay, great. Thank you very much.
Okay,
thanks
John.
for the presentation.
Yeah, thanks.
Charles Clark from Joint Quantum Institute at University of Maryland, College Park and NIST. Charles?
Well, thank you for this interesting talk. You pointed to a phenomenon which I characterized as a tragedy of commons, that of course there's a great expense associated with putting something into Earth orbit, but then the issue of cleaning it, decommissioning it afterwards is really very daunting. I mean, the virial theorem is hard mistress. It's really impossible to shoot things down.
No, you don't want to do that.
So
although
I'm
people
just
have
wondering
tried.
Yeah, but you have to impart about as much energy to the vehicle as it took to get it up there, and it's not so easy to get all that energy in the exact right direction, which is to bring the velocity of the target to zero with respect to the Earth. So I'm just wondering whether there's a public dialogue on I don't know, some sort of pricing to account for the cost of putting something into space that will eventually be into Earth, will eventually become. I don't know how that would be rationally calculated, but is there an international regulatory regime underway to how should I say, prioritize the cost of the external costs of putting satellites into orbit?
Yeah, that's Charles, I mean, you put your finger on an important issue, and it has been discussed in various venues. There is a conference coming up fairly soon called SatCon 2, which is, SatCon 1 was all about engineering and science. SatCon 2 is about policy. And so leading up to SatCon 2, there have been a lot of discussions by the International Astronomical Union. There's a document that they recently issued called Dark and Quiet Skies that talks about this notion. There is a presentation that was made recently to the United Nations. Yeah, the conversation is just beginning, actually, Charles, and I don't think anyone has even thought of stepping up and doing anything specific. The FCC and the ITU actually do require that you come up with a credible way of deorbiting your satellite in a timely way before they issue permit. And they do this, and they're fairly rigorous. So, for example, all of these companies have some way of deorbiting their satellite using some kind of active thrust. The question, of course, as you might imagine, is what if that fails? And the FCC doesn't analyze that. But if it fails, then you're in trouble if your satellite's at 1,200 kilometers, because it's many centuries to decay. If it fails and you're at 500 kilometers, it's a few years, right? 5 years or something, which is almost acceptable. But I agree that you don't want to shoot them down.
That's a very bad idea. The Chinese did that once. It was a mess.
They did, yeah.
And it's a terrible idea. Let me ask a related question from the web. I think we know the answer, but maybe you can also talk to the prospects. It's a question from Scott Wilson, and he asks, are there any regulatory bodies that can make and enforce rules on the optical characteristics of these satellites, or for that matter, any satellites? And assuming that there really isn't one, is there anything in the works, any discussions going on in the background that might progress in that direction?
Yeah. This is, of course, a conversation that's going to really happen in a big way at SatCon 2. Yeah, we've been talking about this for some time, and the answer is no. You can launch something into space and not worry about the effects in the optical. There is no international regulatory body. And as I mentioned, you could shine a very high power laser down on the ground, and nobody's going to prevent you from doing that. It's a free for all. It's a Wild West, actually. And the FCC doesn't have a charter to regulate the optical. It would take an act of Congress, I believe, if I'm right, to change their charter. And that's probably going to happen on, well, I know how fast that works. It was 30 years last time they changed their charter. And so the United Nations has a panel that looks at space as a space environment issue. And as I mentioned, there was a recent presentation to that panel, pretty much watered down from what we wanted. But there is, in principle, a discussion that could occur at the United Nations, but folks there have not even begun to talk about a regulatory arrangement.
Well, a quick addendum to that question is, do you know of any representative or senator currently interested in introducing legislation?
No,
to address this issue?
I don't, but I think I know somebody who does. Not off the top of my head.
Okay.
That is a job I think that the American Astronomical Society has taken on. And I wish them well.
And the new head of NASA, have been any indications from him as to whether this is an issue that
Not that I know of, but that's a very, very good question, actually, Larry. And maybe John has an opinion. I don't know. That's a good question, and I think we should pursue that.
have a question from Carl Merrill, Emeritus NIH Division Director, and very interested in physics as well as bacteriophage and cell biology. Carl?
Thank you. That I enjoyed that talk, and I had a lot of hope for the telescopes that we've heroically built on this planet. But I'm very concerned about the fact there are all these independent groups, as you pointed out, different countries, etc., all launching. And you showed a slide in the beginning with all the satellites that are up there. So of course, what I'm worried about is that they're going to start colliding with each other. Once
Absolutely.
that happens, then it becomes uncontrolled, and you'll end up with an exponentially growing pile of debris that's floating around. And
Absolutely.
I don't know how to get around that. And that's the thing I'm worried about. So I want
Yep. Well, you put your finger on the problem, Carl, and that's called the Kessler syndrome. That, to my knowledge, sets in somewhere around 50,000 satellites in that big region between 300 and 600 kilometers. And so just looking at the current filings with the FCC and the ITU, it looks like we're inching up towards that. And I think that that's probably going to be a limiting factor. And you want to stay well away from that, of course.
I guess the only way to get around that is to build telescopes on the moon and Mars, but that's going to be terribly expensive and dangerous, etc.
And yeah, in addition to the factor of 50 or so more expense, it's also not the right way technically to do the science in many cases. For example, in the cosmic microwave background, we moved into space many years ago with the COBE satellite and then with Planck, etc. But the latest CMB telescopes are all in the ground because of the necessity of having very large phased arrays. And the same is true of something like the Rubin Observatory. You cannot do that in space for various technical reasons. First of all, the data rate's too high. You can't get it down. You'd have to do all your processing on the satellite. It's a very complex system.
We have a question from Frederica Derema, who's former head of Air Force Research Laboratory. Frederica?
Hi, Tony.
Hi, Federica. Great to see you again.
Nice to see you. Yes, as a UC Davis alumna from the physics department, I appreciate very much hearing your presentation and kind of raising all the issues. I asked a question early on, and then you addressed it because you talked about darkening, and certainly in the Air Force, of course, we were very interested for the space debris and increasing kind of space debris, which is doubly affects what you were saying. My question originally was that the number of satellites will increase as we go to 5G, 6G and beyond in terms of increasing the numbers of satellites and the emitted power. And that was before also you talked about the radio astronomy, which is also affected. But then you said also the magic word for me, which is end-to-end simulations to remove the background. So would like to know a little bit what kind of simulations, if you can speak a little bit about that, I would be interested.
Okay, well, you're absolutely right, Federica, that the future is more bandwidth, more beams, higher power, and therefore larger satellites,
Right.
and more of them.
Well, they
all
talk
of
about
which-
CubeSats also, but they introduce other levels of complexity.
Yeah.
You know.
Yeah, but yeah, for this, the sort of the mega constellation industry, I think that
Right.
the only way that they're going to move is up in terms of complexity, power, and size. Yeah, so the simulations that we need to do, that the astronomy community needs to do, haven't all been done. And so we've done estimates in, for example, for the SATCON-1 exercise, for all of the known science cases. And there's a astronomical journal article that we published on this, all the known science cases. And some science cases, as I mentioned, are not as affected as others. But all these different science collaborations, and by the way, there are eight science collaborations for the LSST survey. They all have to take ownership of this problem and find funding to do full end-to-end simulations of the impact on their science. We can estimate it, but in the near future, we really want to know more precisely of what the exact systematic errors are. And if you know that, then as you know, you can begin to invent ways to mitigate them to some extent. And so that whole process is just beginning now. It's going to take a lot of people who would have to, step away from what they're doing in science and do this chore. And so it's going to take just the right kind of people that aren't interested in publishing all sorts of scientific articles to do this kind of stuff.
So can I ask a follow-up question, please? So who would fund this work? And number two, at AFOSR, we funded a lot of simulations for space debris. Then at NASA, and I know Mike Seablum, who was the chief scientist for the Science Mission Directorate, I wonder if the funding, and of course NSF, the funding for this work maybe needs a coordinated effort.
It does. And so our observatory is funded both by the Department of Energy, Office of Science, and the National Science Foundation Astronomy Division. And they're both interested in funding some of this kind of research, but as you know, the way they fund science is different. And so some of us have little grants from the NSF to pursue some aspect of this. I know that the DOE is considering pouring some effort into this as well.
Yeah, well, maybe we can talk offline because there may be an opportunity for collaboration, bring NASA and AFOSR with NSF, because, I understand what you say, these things are funded piecemeal and serendipitously kind of not coordinated.
Yeah, and the space, you alluded to it, but the space situation awareness folks are also quite interested in this, primarily because of the Kessler syndrome issue. And they're also, since they're interested in it, they're also pursuing it. They have funding.
Right. Yeah, we funded from AFOSR, and certainly some of the FRLs are interested. So maybe we can talk offline.
Yeah. Okay, Frederica. Great.
Yeah. Thank you so much. Nice to.
Yeah.
A quick follow-up question. Does National Academies convene a panel? Have they been asked to look into this? They have a role to play here.
I was asked to give a presentation to the astronomy section of the Academy at our last meeting just a couple of weeks ago. And so a conversation has started there. And we haven't got to the point where we have asked for a special panel on this, but it's something that the NAS could conceivably do.
I have a question from Ferris Essam, two questions, but I think they were already answered. So Ferris, if they haven't been answered, you can re-enter them, but I'm going to not ask them because I think they were already answered. Al Ehrlich has a question. It's somewhat amusing. Al? Al is a physicist who was at NRL for many years.
Yeah, I see your question, Al.
I may have missed it, but SpaceX seems very cooperative. Are they being funded to be cooperative, or is this?
Yes. So as I mentioned, I reached out to people that I actually know at SpaceX, and immediately got their interest and cooperation, and then I found myself talking to the boss for some period of time, and that has mushroomed into an actual department where they are looking into this with a bunch of engineers, and so they do want to do the right thing. The trouble actually is that it's a very complex engineering challenge.
Yeah. How about other agencies and organizations which launch satellites? You would need their cooperation too, wouldn't you?
Would definitely, and I think, frankly, to be honest, I think it's the court of public opinion that is going to rule at the end of the day, and that if some company like SpaceX can be seen to pursue responsible citizenship in near Earth orbit, then maybe they will be encouraged to do so. But in the business world, that usually is not enough. In my limited experience at 35 years at AT&T, you need to have a bit more than that. And I have talked to several of these other companies and several of these other countries. And you can avoid the FCC if you would like, if you incorporate your company somewhere else, like French Guiana.
Okay, I was afraid you'd answer the question somewhat like that. Thank you very much.
Okay, Al, good talking with you.
Good talking to you.
So I think we might end with one question here. It's a more general question, and or maybe two questions. Which is more detrimental to astronomical observations, light pollution or LEL satellites? This is a question from Michelle Black on YouTube.
So up until 2019, I would have said light pollution. That is to say, we built our observatories to be very far away from lots of sources of light, and of course on top of high mountains in special places where there are no clouds. And in the radio, of course, the same thing has happened, where we build radio observatories in quiet places away from, in Western Australia or somewhere. And even if it's in the United States, we prevent people from having microwave ovens anywhere near the telescope. However, and so there are these quiet zones in both the radio and the optical. And up until 2019, that was going pretty well. But now you have satellites going overhead, and there are enough of them that there's no place to hide. That's the problem.
So in part, if I understood some of your charts, the problem is that they're not very good neighbors. They can't tailor their broadcast frequency tightly enough to prevent it from spilling over.
There's issue actually, and there's an even bigger issue that you can't, for a reasonable amount of money and weight, build a transmitting phased array antenna that has their side lobes down by 80 or 100 dB. You just can't. It's not cost effective.
And you don't see a technical fix for that.
No. We can go and re-engineer a lot of our radio telescopes at great cost to reduce the side lobes a little, but not by that much.
We have another question from Charles Clark, which I think will be our last question. I did have a question.
Thank you, Larry. Am I audible?
Yes.
Well, thank you, Larry. Well, pursuant to the previous question, the nominee administrator for NASA has traveled beyond the von Karman layer, and according to testimony I recently heard on C-SPAN, he considers that place to be his own backyard. So it might be that he, if confirmed, he'd be quite receptive to proposals for research on cleaning up this problem from a technical perspective.
Yeah, that's an interesting idea, actually, Charles. So we should pursue that. That'd be great.
I have a technical question. You said your favorite unit is electrons per pixel.
That's my favorite unit, and it's
That's what you said.
nobody else's. It's nobody else's favorite unit.
But I thought it would be photons per pixel.
Oh,
Photons.
it is. It is at the end of the day. But the thing that damages the image and that creates havoc in the camera is the charge per pixel. That's so you have the satellite moving across the satellite image moving across the focal plane. It spends very little time on each pixel because of its motion, its angular motion. But while it's there, a certain number of photons hit that part of the sky that the telescope is looking at, and those photons get focused down onto the pixel through a filter and the telescope optics. And eventually, through the quantum efficiency of the detector, create electron hole pairs. And it's these electrons that we measure the camera response in terms of.
Yeah,
It's just a convenient unit only for camera builders.
Sure. I just
not for astronomers.
wondered how many electrons you get per photon. Is it a
One is typical.
Okay.
Yeah, you can get quantum efficiencies that are that high.
And it's not per unit time.
Well, it's during the exposure. So, it's
That's what I thought. Yeah.
whatever. Yeah. So there's the sky. It's always there during the exposure. And of course, the sky is not dark completely. And so it's building up electrons all over the image sort of uniformly. And so that's the sky background. And then on top of that is the satellite and the stars and the galaxies.
Last question. Would it help if all these constellations were lower?
Yeah. Again, they would be
Put them in 100 kilometers? I'm just making that up.
Well, so there's a problem there in that they would actively deorbit, and you'd have to pour a lot of energy into keeping them there. So that's not a good idea technically.
It was a theoretical question.
But yeah, in principle, because then of course they would be shielded by the shadow more, and so twilight, we could observe in twilight without seeing as many of them. But the problem with having them lower also is that there's a 1/r² effect. So they're going to be brighter in the radio.
Right, 4 times.
And it's probably counterproductive if you're using them for radio, because you want to be high enough to throw a beam all over the US to steer it around to where you want it. And you can't do that if you're really low.
I think that's a wrap. Really appreciate the time you've taken.
Yeah, it's great talking with you all.
Lecture and to fill these Q&As. And as I've said, you're hopefully going to be in DC at some time in the future and join PSW for, or some of the folks from PSW for reception and dinner. And
Yeah, I would. Yeah, it would be an honor, and I look forward to that when I can start traveling again.
Yes, and we will too. So thank you very much.
All right. Okay, Larry, thank you.
So a few announcements before we go. Recording of tonight's lecture will be available to everyone on the PSW Science YouTube channel and in due course on Vimeo and via the PSW Science website. I should also add, for those who might be interested to learn more about the Rubin LSST Observatory, The PSW lecture at the 2361st meeting was on the Rubin Observatory and was given by Observatory Director Stephen Kahn. A video of the lecture is available on the PSW website and on the PSW YouTube and Vimeo channels. Please share the links to this video with your friends and subscribe to the YouTube and Vimeo channels for notifications of new postings, and to PSW on Twitter and Facebook for news and updates on the Society's activities. And join. It's easy to apply for membership using the Join button on the PSW Science website. The next meeting, number 2441, will be in 2 weeks on May 21st. The speaker will be Bill Powell of the State University of New York College of Environmental Sciences and Forestry. He will be speaking about the chestnut blight and approaches to creating and bringing back a blight-resistant American chestnut. The 2442nd meeting will be on June 4th and will feature the annual Joseph Henry Lecture. The speaker will be Carlo Rovelli, director of the Quantum Gravity Group at the Center for Theoretical Physics in Marseille, France, and distinguishing visiting research chair at the Perimeter Institute. He will be speaking on quantum gravity. The 2443rd meeting, capstoning the spring lecture series, will be on June 18th. The speaker will be Steve Stitch, program manager of NASA's Commercial Crew Program. He will be speaking on the US Commercial Crew Program and human spaceflight. Any changes to the spring lecture series, should there be any, and lectures coming this fall will be posted to the PSW website. Check there often for updates. And finally, please join me in thanking tonight's crew, James, Ann, and Robin, for producing tonight's event. I will now adjourn the 2440th meeting of the Society. I wish everyone a good evening. The meeting is adjourned.